Hi, thank you for watching this talk. My name is Matt Clement, and I'm a postdoc at Carnegie EPL in Washington, D.C. And I'm going to talk about some work we've been doing recently trying to form better Mercury analogs in terrestrial planet formation models. So as a quick review, there are a few things that we would like our late-stage terrestrial planet formation models to match about Mercury analogs specifically, but also about its particular relationship with Venus and Venus's formation more broadly. It goes without saying that Mercury is the smallest planet, but what's more peculiar is that if we neglect Mars and Jupiter with the asteroid belt in between them, the Mercury-Venus mass ratio is by far the most extreme of any pair of neighboring planets in the solar system. And exoplanet demographics seem to indicate that closer to unity mass ratios of neighboring planets are a more typical outcome of the broad planet formation process. In a similar manner, Mercury's dynamical separation from Venus in terms of their mutual period ratios starkly contrasts those of the other terrestrial planets and is far more similar to the dynamical separations of the outer planets, which were likely acquired via mutual encounters during an epoch of instability. So this is something we would like our models to match as well. Of course, Mercury's bulk composition and structure is quite different than that of Earth, and presumably Venus and Mars as well. Mercury's core makes up 70 to 80% of its total mass. So this is something that if we can track in our models, we would like to be able to match as well. And finally, Mercury possesses a moderately excited orbital eccentricity and inclination, which are also the largest of the 8 planets. It turns out this isn't very difficult to do and is extremely common outcome of the giant planet instability. So this might be much more of a loose constraint for our models that are specifically investigating the formation of the terrestrial planets. So studies of the late stages of terrestrial planet formation are quite prevalent in the literature over the past 20 to 25 years, since advances in computing power make such investigations feasible. So in the so-called classic model of terrestrial planet formation, which is being displayed in this video here with semi-major axis on the x-axis and eccentricity on the y-axis, a small number of larger Moon to Mars mass planet-forming embryos embedded in a sea of smaller planetesimals possessing a roughly uniform solid surface density profile combine and accrete over 100 million year timescales. Simple model is highly successful at replicating many bulk features of the inner solar system. For instance, it typically forms 4 planets roughly where they're supposed to be. So most modern models really don't deviate too far from this general picture of late stage collisional assembly. The first problem with this model is the Mars analogs formed are too massive by around an order of magnitude or so. This has received a ton of attention over the past decade or so and really isn't so much of a problem anymore beyond debating which model or combination of solutions are the right ones. So I won't be fixating on this discussion in this talk. Now, just like Mars, this classic scenario also has an even bigger Mercury problem. Really, none of the proposed scenarios are able to match those broad properties I laid out in the first slide, particularly the Mercury-Venus mass and orbital period ratios. So this is the first in a series of plots that I'll show that depicts the Mercury-Venus period ratio on the x-axis and the mass ratio on the y-axis with the red star denoting the solar system value. Those 6 points are the only Mercury-Venus systems formed in 100 simulations of this classic model of terrestrial planet formation, which throughout this talk, I'll be defining that system as any simulation that forms exactly 2 planets inside of 0.85 AU with the inner one less massive than the outer one. So in this model, Mercury forms just the same as Earth and Venus from the ground up right where it is today. And a big reason there are so few points here is oftentimes Mercury is more massive than Venus, or more commonly, you only end up with 1 massive planet in the Mercury-Venus region. So obviously, Mercury's unique makeup implies it formed in a slightly different manner than the other terrestrial planets. Sometimes referred to as an impact origin for Mercury, this video is showing terrestrial planet formation starting from the same exact classic initial conditions, except here we're introducing collisional fragments and falling collisions that occur at geometries that would not be perfectly accretionary. This video I've color-coded the fragments green. So there are 2 main objects, or 2 main options for an impact origin for Mercury. Either Mercury is the target that gets hit by a smaller projectile, thus eroding the majority of its once large silicate mantle, or Mercury is the projectile and undergoes a hit and run collision with a larger object, presumably proto-Venus or proto-Earth, and goes on to reaccrete from the disrupted material in a manner such that it attains a large core mass fraction. So obviously, these types of simulations aren't necessarily tuned to specifically generate the ideal impact geometries that we think will give us a good mercury forming impact. Instead, they're looking to see if these types of events are common in a classic model of terrestrial planet formation. And the quick answer is no, they're not. As you see, this process does give us more mercury analogs as I'm plotting the same number of simulations. We're starting to approach the red star, but the problem really is that you need an impactor with a fairly extreme orbit in terms of its inclination and eccentricity to get a good mercury forming impact. And those geometries are not common occurrences in these models. Now, it's also worth mentioning that Mercury could have formed small in the same manner as Mars. So a compelling solution to the small Mars problem, invoked by many of the leading models, involves concentrating the terrestrial forming disk in a narrow annulus. So rather than forming directly at 1.5 AU, Mars ends up getting kicked out of this concentrated region and stranded at its modern orbit. So in the same manner, these models occasionally, though not as frequently as for Mars, scatter an embryo inward and yield a good mercury analog. This particular simulation is also using collisional fragmentation, and here I've color-coded the fragments pink. As you see, this is a nice example where it's actually a collisional fragment that ends up surviving and becoming the resulting mercury analog, although this object finishes the simulation on a crossing orbit with Venus and is thus not long-term stable. That leads to the big problem with these Annulus models, which I've added to this Mercury-Venus period mass ratio plot in blue and green. These simulations do a much better job at getting you a small Mercury. However, they still are not able to match the Mercury-Venus period ratio. And oftentimes, the most successful outcomes, for example, the blue point in the upper left corner of this plot, finish with the Mercury analog on a crossing or near crossing orbit with Venus that will eventually lead to a collision between the two planets in the next billion years or so. An additional possibility that is certainly can't be neglected is the influence of the giant planets. This plot on the right is made by taking Mercury and moving it around in the modern solar system within a grid of initial semi-major axes and inclinations. Each box is color-coded by the maximal change in Mercury's eccentricity over a 10 million year simulation, which gives you a sense of the rich dynamical environment in the innermost regions of the solar system. In particular, the real Mercury, which is shown with the red star, sits on top of a small quiescent island of quasi-stability in between secular resonances with Venus and Jupiter. These resonances were not in the same location when the planets formed. In particular, the new 5 secular resonance with Jupiter's eccentricity vector precession, which the green arrow is showing, jumped through the inner solar system during the giant planet instability. So when we study the process of terrestrial planet formation ensuing in conjunction with the giant planet instability, as shown by this video, occasionally some interaction with the forming Mercury and the traversing new 5 secular resonance results in a decent replication of the modern Mercury-Venus period ratio. So here I've added some instability simulations in pink, and you see now there is one point on the far right that actually gets the dynamical separation correct. So while we still have no examples that meet or exceed the red star in the upper right corner, at least now we have some points exceeding the solar system point on both axes. This is to say that we have one or more mechanisms that can replicate the period and mass ratios occasionally, albeit not at the same time. Another option that has been proposed going back as early as 2001 and has resurfaced in some nice work recently published by Patrick Likauka is to experiment with the surface density profile and embryo masses in the Mercury forming region. These are sometimes referred to as peak disk models. As you see in the plot, the terrestrial forming disk is essentially peaked or fine-tuned in order to ideally replicate the exact masses and semi-major axes of the 4 planets. Fortunately, though, these models still tend to form overly massive Mercury analogs that are still too close to Venus. So in spite of all efforts made, we still do not have a working model capable of replicating the precise Mercury-Venus system. However, I'd like to put a major caveat on this entire discussion, as I'd be remiss not to point out that the majority of the simulation sets I'm showing here really are not designed to replicate Mercury. Mainly, this is a consequence of the fact that nearly all of these models utilize embryos that are often of order the mass of Mercury or larger, and also truncate the terrestrial forming disk outside of Mercury's modern orbit. Now, while this may be loosely physically motivated, it really is more a choice made to save compute time, as it is expensive to resolve the orbits of objects interior to Mercury in these simulations. However, as I mentioned before, we do now have a series of promising mechanisms that we can experiment with and try and generate the precise Mercury-Venus system. In particular, using codes that are built to handle fragmenting collisions and track hit and run and repeated hit and run encounters have shown promise in generating Mercury-like core mass fractions. Additionally, some degree of mass depletion in the Mercury-forming region is probably important, as well as the aforementioned perturbations from Jupiter that shouldn't be neglected. So we started a series of projects that I'll briefly go over to try and explore these processes further. And the first thing I'll talk about is the possibility of direct in situ formation from a mass depleted region of material interior to Venus. This video shows an example of a simulation that, like this, that formed a very successful Mercury analog, and we were tracking collisional fragments in this video, again color-coded green. So we tried to do a broad parameter space search to find the structures of this additional component of material that best produce Mercury analogs. For the total mass, the Mercury region, we found more moderate masses, like about a Mars mass or a little bit more to be more successful. If the inner component's too massive, you obviously form a Mercury that is too large. However, if it is under mass, Venus ends up eating all the material and you form no Mercury. We also experimented with the distribution of material in terms of the amount of mass locked in larger embryos and that embedded in smaller planetesimals. We found slightly larger total planetesimal masses to be more successful, as the added dynamical friction and gravitational interactions with planetesimals helps to essentially isolate Mercury and decouple its formation from Venus's. However, this was just a minor effect. And finally, we varied the slope of the surface density profile and found shallower slopes tend to be more successful, again, preventing Mercury from getting eaten up by Venus. You can see here, while we do form a bunch of bad Mercury-Venus systems, several of our results from these more ideal combinations of parameters are extremely compelling. It's also worth pointing out that this is a more orderly genesis for Mercury, and while we do occasionally get final planets with boosted core mass fractions, the impact geometries tend to disfavor massive structural augmentation like an impact hypothesis. So this would imply that the planetesimals in the forming region already possessed enhanced iron contents, and there are several promising mechanisms for this that have been proposed before, including the photophoretic effect, magnetic aggregation, or some advantageous positioning of a primordial snow line. So the next project we had going was more geared towards experimenting with ways we might be able to use Jupiter's influence to strand a Mercury analog on an isolated orbit. This idea hinges on how unstable this orbital parameter space is near to the new 5 resonance. If you set Mercury down, like is being shown in this plot, right on top of this resonance, you can get all sorts of wild evolutions. So we hypothesized that instead of just Mercury there, you once had a quasi-stable chain of Mercury-sized objects interior to the other planets. As this video shows, it's very easy for this chain of protoplanets to cataclysmically self-destroy because of perturbations from Jupiter. And through this process, we get tons of high-energy fragmenting collisions that efficiently alter the core mass fraction of Mercury analogs. And what is being shown here on the left is the cumulative distribution plot of core mass fractions for several different simulation sets. In over half our simulations, we finished with 1 Mercury analog inside of Venus with a core mass fraction that's boosted greater than 0.5, and many have values approaching that of actual Mercury. The problem that you can see on the right, however, is that Mercury almost always finishes inside of the modern location of new 5 with Jupiter. So we place Mercury on an orbit that's essentially too far from Venus. We think a solution to this would be if the process happened during the migration of new 5 during the instability. We're testing that now. I'm going to finish by putting my conclusion slide up that feel free to read. And again, thank you so much for taking the time to listen to this talk.